Despite the massive boom in artificial intelligence and supercomputing, global industries have hit a hard computational and physical wall. Traditional computers cannot perfectly simulate the chemical reactions inside a next-generation battery, and standard sensors often fail to see microscopic metal fatigue or unmapped pipes buried beneath our streets. Without tools for exact simulation and measurement, developers are stuck in a cycle of physical trial and error, building and testing prototypes because they cannot yet model the subatomic reality of their products. Quantum computing changes this by utilizing qubits. Through superposition and entanglement, these units allow a system to explore millions of computational possibilities simultaneously, rather than checking them one by one. However, the same physics that provide this power also make the hardware incredibly difficult to control. This is the challenge of the noisy, intermediate-scale quantum era, where systems are often too unstable for practical work. Even the slightest thermal fluctuation or a single stray photon can cause decoherence, instantly destroying a quantum calculation. Because these systems were so fragile, quantum technology remained a delicate lab experiment for decades, unable to survive the vibration and noise of an industrial environment. That changed with the recent transition to fault-tolerant quantum computing, driven by a breakthrough in error correction. Engineers grouped unstable physical qubits to form a single stable logical qubit, allowing the system to correct internal errors in real time. As these scale on chips like Google's Willow, error rates plunge rather than multiply as more qubits are added. This shift has moved quantum hardware out of the realm of theoretical physics and into the world of disciplined systems engineering. These stable systems are now moving into industrial server rooms, with pharmaceutical and chemical giants like BASF using them to analyze molecular structures. By removing the mathematical approximations used by classical computers, quantum hardware can execute exact molecular simulations, helping researchers design new medications and green catalysts with higher precision. In logistics and aerospace, firms use hybrid algorithms to coordinate global fleets and find optimal robotic paths, tasks with too many variables for standard supercomputers. Across the global supply chain, these exact digital simulations reduce physical prototyping and logistical guesswork. Quantum effects are also being used to capture data from the physical world. While computers process information, quantum sensors use subatomic particles to gather it. Quantum gravimeters drop ultra-cold atoms in a vacuum to measure subtle shifts in gravity, mapping hidden tunnels without digging. Microscopically, flaws in diamonds detect magnetic shifts from nanoscale metal fatigue, identifying structural weaknesses before a physical crack ever appears. These sensors help eliminate physical blind spots, allowing industries to monitor their infrastructure with total awareness of the environment. Because the hardware is now stable and predictable, quantum capabilities have become active line items in corporate procurement budgets. Most businesses follow a clear acquisition ladder, starting with cloud access for initial testing, moving to reserved priority access for research, and finally installing secure on-premise systems for strategic operations. Organizations are no longer waiting for a distant breakthrough. They are integrating quantum tools to match their current operational readiness. In practice, these tools complement existing AI. While machine learning is used to find patterns in data, quantum computers explore the billions of combinations within those patterns to find a solution. This creates a path toward a compute-first model for industry. By simulating nature at its most basic level, developers can use quantum technology to validate their designs with mathematical certainty before physical production begins.